The leptogenesis is the one baryogenesis model to explain the baryon symmetry of the universe. And today I will talk about the several leptogenesis model with the further analysis and extension as a journal review. This video is based on the various recent paper. I attached the reference in the final part. So the first topic is leptogenesis with the multiple happy neutrino or right-hand neutrino, RHN. In the standard leptogenesis, the washout parameter, capital K, is defined as light here between the decay light and the Hubble at the temperature zero with the RHN scale. And this washout parameter, capital K, is strongly related with the size of the equal coupling Y and the happy neutrino mass scale. And to obtain the large Shipyard symmetry and the enough asymmetry generations for the observed value of the BAU, the Shipyard symmetry epsilon should be the large, and also the leading temperature should be the large. Then this yield that the low bounds of the happy neutrino mass as a 10 to the 9 GeV, which is called Davidson-Ibarra bound. But one can consider that the multiple happy neutrino, then now the active neutrino masses are determined by the such a multiple contributions of the happy neutrinos with the index I. So the for fixed active neutrino mass mu, the equal coupling size are distributed among the multiple sides. So the equal coupling size becomes a small, is proportional to the inverse of the number of the happy neutrinos. So the washout parameters can be small. So such multiple happy neutrinos makes the system becomes the weak washout, the smaller k, naturally. So the generator symmetry cannot be erased significantly because the leptogenesis is in the weak washout. But the total lepton symmetries comes from the decay of the multiple happy neutrinos. So as a result, the observed baryon symmetry can be reproduced with the small happy neutrinos. So the point is the multiple happy neutrinos make that the equal coupling size become small, and also the washout parameters become small. So the generators of symmetry cannot be erased, and this can be lowered down the bound on the happy neutrino mass as 10 to the 7 or 8 GeV. The next topic is the memory effect from the weak washout. We can consider that the 3 RHN leptogenesis with the specific hierarchy. The lightest happy neutrino N1 contributes to the binary B minus symmetry, but the heaviest type erases this asymmetry by the washout process. This assumption is valid when all the decay parameters K1, K2, K3 for the N1 to 3 are in the strong washout regime. These parameters are larger than the 1. So inverse decay and the RMV scattering wash out the asymmetries. In this case, the binary symmetries are just determined by the B minus zero symmetry coming from the lightest one and one. But one can consider that if the heavy neutrinos tides in the weak washout regime, the K2 and the K3 are smaller than the 1, then the decay of the N2 and the N3 that does not occur significantly. So the erasing the asymmetries process is efficient. So the effects of the N2 and the N3 is important. So the binary asymmetry is also determined by the effects of the N2 and the N3. So the weak washout regime for the heavier state makes the additional contribution from the N2 and N3 without the efficient washout. This is called the memory effect. So far we talk about the leptogenesis with the multiple state by considering the small washout parameters k, so that the having neutrinos in the wave washes out, so the erasing the symmetry generations that becomes insufficient. Now we turn to the leptogenesis with the additional cosmological perturbation effect. And one can consider that the cosmological density perturbation, some spatial local part, the temperatures fluctuates, then this can change the dynamics through the lepton asymmetry generation. The equilibrium density of the happy neutrinos are proportional to the Boltzmann factors. But now that the temperatures fluctuates with the small quantity delta T. And such a size of the temperature fluctuation is the order of the 10 to the minus 2, and that is changed the behaviors of the leptogenesis. The leptogenesis are governed by the Boltzmann equation. The first ones for the having neutrinos number density, and second ones for the B minus L symmetry. And now the temperatures are fluctuated, so the time variable z, which is defined by the ratio between the neutrinos and temperatures fluctuates. So here the Zt now contains the temperature fluctuation. So effects of the temperature fluctuations are now inserted for the several terms in the Boltzmann equation, for the decay term, washout term, and the equilibriums number density. And also the gravitational potential with associated with density perturbation is also added as a capital precisely in the differential equation. For the such a local fluctuation, this makes the earlier breeze out of the happy neutrinos compared to the homogeneous case. So the such earlier breeze out makes the enhancement of the asymmetry. So this is the homogeneous case with the zero temperature fluctuation, and if one averages the final symmetry over the space, then the B minus symmetry with the temperature fluctuation makes the earlier breeze out and the enhancement symmetry. The order of the enhancement is the roughly the 1.2 to the 1.3 with the density fluctuation with the fractions of the 10 to the minus 2. So this can change the parameter space for the thermal leptogenesis and can relax the low bounds of the RHN mass. Now we turn to the leptogenesis with the other seesaw mechanism. Already we talked about in the previous video, there are several neutrino mass model as extensions of the seesaw mechanism. There are linear, inverse, and double seesaw model with additional fermion or additional scalar. Such a habitual styles makes the pseudo-Dirac pair. In the general seesaw mechanism, there are just two mass, the Dirac mass term of diagonal term, and having neutrinos as the minor mass term, but there is additional term in the extended matrix component, and due to the mass hierarchy, this makes the pseudo-Dirac pair, and this leads to the small LMV parameter. And also the pseudo-Dirac pairs makes the splitting of the mass eigenvalue is quite degenerate, and that this might satisfy the resonance condition for the CP symmetry. So the resonant leptogenesis can be naturally established by using the such a linear inverse stable seesaw mechanism. Also, we can consider the other types of the seesaw, unlike the type 1, In the type 2 seesaw, there is S2 3 plus color, capital delta. So the decays of this 3 plus color to the lepton blood or Higgs blood can generate the lepton asymmetry. Also, the one can consider that the Dirac leptogenesis, unlike the Manara term, because the Dirac mass term is exact lepton number conservation, so the this does not generate the net lepton number. But now the symmetries are generated between the different structures. In the Dirac neutrinos model, the total lepton numbers suggest the conserve, but this can be decomposed as a left-handed active neutrino part and right-handed neutral neutrino part. The total lepton numbers conserve, but the left-handed and the right-handed part might violate the lepton number. So the observed visible part, the baryon symmetry is just proportional to the left-handed part, because only the left-handed neutrinos that participate in the standard model interaction. So this is just a similar explanation, and also the equilibrium process between the left-handed and right-handed symmetry, and we can connect this Dirac leptogenesis with the two different structures to the asymmetric dark matter. Such asymmetric dark matter ADM models are motivated by the similar number density of the dark matters and the baryon. The observed Lillig abundance of dark matters and the baryon has the order of the 5. And to obtain that, we know that the proton mass for the baryon, the ADM mass is the order of the ZB. And now the this asymmetry in the right-handed part becomes the asymmetric dark matter structures, and the left-handed part becomes standard model. So the Dirac leptogenesis can naturally be connected to the ADM model. Now we turn to the leptogenesis with the other color, especially the this color get the spontaneous symmetry breaking. This makes the eventually the spontaneously baryogenesis with the is Goldstone boson, because such a spontaneous symmetry breaking makes the NGB mode by the Goldstone theorem. For example, the capital pi generates the Manara mass term by its symmetry breaking. The radial part just gives the back, but the angular mode is the NGB mode. It corresponds to the Maron. So now the B minor symmetry is the breaking here, and the angular part, this Maron build, is coupled to the B minor cell current. So the kinetic term of this Maron build generates the effective chemical potential. So first of all, this Lagrangian comes from Maron and the B minor cell current coupling, because the spontaneous symmetry breakings ensure that the natural interaction between the NGB boson and the breaking symmetry currently associated with the breaking symmetry, and So by this interaction, we can obtain the effective chemical potential from the kinetic term of the Angevin. And such effective chemical potential from the kinetic Angevin change the Boltzmann equation contributions from here. The Laplace asymmetry can be generated via the motions of the Angevin or Myron mode without the decay of the specific heavy particle. Such a kinetic Myron scenario, we can characterize the quantity, the ratio between the theta dot and entropy density. Also, this can explain the dark matter abundance naturally, and generated asymmetries that does not come from the decay, so that we can avoid the well-known low bound on the right-hand nuclear mass. Also, such a discussion can be extended to the about the U1 peak symmetries with the action. Now that here's the Angevin mode becomes the action here, and where this is the NTW is the domain one number. And this also the actions are coupled to the current associated with the U1 PQ, and the kinetic term of the action angular field generalize the effective chemical potential and eventually makes the asymmetry. So today we talk about the further analysis of the leptogenesis with the several extension. First of all, we talk about the multiple happy neutrinos. Some of them are in the weak washout. Then this can relax the low bounds on the happy neutrino mass, because the erasing the symmetry becomes inefficient for the weak washout regime. And also the density perturbation can change the Boltzmann equation. The generated symmetry can be enhanced with some several order. And also we can discuss the leptogenesis with several extensions of the seesaw mechanism. Especially this contains the Schroeder-Dirac pair, which can naturally establish the resonant leptogenesis. And finally, we talk about the connection between the Dirac leptogenesis and the asymmetric dark matter. The total lepton number is conserved, but the generated asymmetries are stored for the lap-handed part, and the summons are transferred to the hidden structures like the ADM. And the leptogenesis can be driven by the kinetic motions of the Nambu-Goldstone boson, which is associated with the spontaneous symmetry breaking. This makes the effective chemical potential and generates the lepton asymmetry rather than the case of the heavy particle. So today's videos are based on the several references of the recent works on the leptogenesis with the several extensions, and I attaches the related reference. The first two ones are related for the multiple heavy neutrinos, and the third ones for the leptogenesis density perturbation, and the next two ones for the leptogenesis with other system framework. And the next ones for the connection between the Dirac leptogenesis and asymmetric dark matters, and the final two ones discusses about the leptogenesis driven by the kinetic motions of the Angevin field.